Let's have a look at continuity and limits. Let's make a function that is basically a parabola up to, say, x equals 1. So that's 1 as well. And then for values greater than 1, it's going to have a value of a half. So what happens when x equals 1? I can choose which do I want. It doesn't really matter. So let's say it's going to have a value of a half when x equals 1. Notice the terminology, the open circle and the filled in circle. This lets me know that when x equals 1, that's my value, not that one. And additionally, let's say the value at 0 is also going to be a half. So here's our function f of x equals a half for x equals 0, a half for x greater than or equal to 1, and x squared otherwise. Remember, functions don't have to be nice. The only key thing is that for every x value, the function returns a corresponding y value. Why do I choose this example? Well, because it illustrates f is continuous, say, in this region from here to here. But it's discontinuous at x equals 0, and it's also discontinuous at x equals 1. And why have I drawn two separate discontinuities? Well, this one is a removable discontinuity. I could simply replace that point back there, and now the function would be continuous at that point. But this one I can't. This is a non-removable discontinuity. So what does continuous mean? Well, basically it means zoomable. Our function is continuous at this point. Basically means we can keep zooming in and we're never going to get any jumps. We're always going to be able to find smaller and smaller rectangles centered around this point where the function enters through one side and leaves through the other side without ever going over the top or under the bottom. So you set your y range as precise as you like, 0.0001, whatever you like. Here's our y range, either side of our y value. See, this is setting here and here. This is my Y range. I can always find some delta band around this point. That gives me that rectangle. I can always find some delta band around my X value, which maps to within this epsilon band. Yes, so for any epsilon band, around f of x naught, we can find there exists some delta band around x naught which maps into that epsilon band. Intuitively this makes sense. We say I want my rectangle to be 1 millimeter high, and yes, I can find a corresponding width to get this image. I specify 0.0001 millimeters, and again I can always find a corresponding width that will put the function within that rectangle. So intuitively it makes sense, but to make it robust, let's define a discontinuous function and then negate that to get a continuous function. So for the purpose of illustration, I will choose a really simple discontinuous function. What's the simplest one you can imagine? Well, probably if it's -1 here and +1 here, you're not going to get much simpler than that. And what's its value going to be at 0? I've kind of got 3 possible candidates. I'm going to choose that one. So f of x is 1 for x greater than or equal to 0 and -1 otherwise. Now this is obviously discontinuous. We can put an exclusion zone around f of 0, and you can see clearly that any delta band around 0, doesn't matter how small, it's always going to contain some -1 values, as well as some +1 values. The +1 values are okay because they're within the wiggle room, but these mean that this delta band is failing to map to within this epsilon band. So discontinuous is equivalent to saying there exists some epsilon band around f of naught, well, in general f of x naught, such that all delta bands around x naught fail to map within that epsilon band. i.e., we can make an exclusion zone where any delta band is going to fail to map to within that exclusion zone. So if it's not discontinuous, it's continuous. So continuous is the same thing as not discontinuous. Which means there doesn't exist such a band. i.e., for every epsilon band, you can find a delta band that will map to within it. For every epsilon band around f of x naught, you can find delta band that maps to within it. We can write this formally and say for all epsilon, obviously greater than 0, there exists some delta greater than 0 such that if our x value is within delta of x naught, so it's somewhere in this region, so the distance between x and x naught is less than delta, implies that the distance between f of x and f of x naught is less than epsilon. And that is our formal definition of continuity. Okay. can you see this is why we've been using x0 and not x all along? Because we're saying we pick an arbitrary point x that is within delta of x0. So here's our x, and if you subtract these two values and take the magnitude of that, you get the length. So this length is less than delta, means that, let's follow it up to there, means that this length is less than epsilon. So we've defined continuity at a point x0. So we should have been writing discontinuous at x0 and continuous at x0. So now we define continuity over an interval, continuous over an interval a, b. It could be open, it could be closed, it could be half open. I'll make my interval half open just as an example. So it's continuous over that interval if and only if it's continuous for all x in that interval. Let's call that interval I, and e.g. the closed interval from 0 to 1, or the half open interval from -1 to +1, etc. So it's continuous over that interval if it's continuous for all x in that interval. Maybe I should write x0 just to be consistent with what I've written already. Notice I'm interchanging the is equivalent sign and the double implies and is implied by, and if and only if. They're all the same. It's just linguistic preference, whatever feels right in the moment. So another way to say this is f continuous at x0 if and only if as x approaches x0, f of x approaches f of x0. So as our x value approaches this point, so our y value approaches this point. And you can see here that doesn't hold because, well, this is 0. What is f of 0? It's 1. So as x approaches 0 from above, f of x does approach f of 0, tick, but as x approaches from the negative direction, as x tends to 0 from the negative direction, f of x isn't going anywhere close to f of 0. f of x is sticking at -1. So f of x is failing to approach f of 0. So therefore this does not hold, because it's conditional on the direction of approach. And for this isolated singularity, it's not going to work for either direction. Both directions it's converging to 0, but the actual value is 1. So it's saying as x gets arbitrarily close to x0, f of x gets arbitrarily close to f of x0. What if it didn't? What if there was some exclusion zone around f of x0 where f of x never got guaranteed within that exclusion zone? It kept spitting values outside of that exclusion zone. Then we would have a discontinuous function. Another way of defining continuity is to say f is continuous at x0 if the limit as x tends to x0 of f of x is equal to f of x0. And we should really say this limit exists and is equal to f of x0, because maybe that limit doesn't exist. In this example, the limit doesn't exist, because as we approach from below, the limit is -1. If we approach from above, the limit is 1. So let's look at a couple of interesting examples. Firstly, let's make a function that is continuous nowhere. How can we do that? Well, what if we had a function that was 0 for rational x, x in the quotients. Quotients are things like 1/3, 17/1, -2/7, etc. Whole numbers and fractions. So it's 0 if x is a quotient, but it's 1 otherwise. We could have written that as if x is in the reals but not the quotients. If we wanted to. So can you see for this function, if we look on the number line, we're interested at a particular point. Now, is it continuous at this point x0? So either x0 is a quotient or it's not. So either the value is up here or the value is Maybe I should have made -1, just so I give myself more space to work with. So, or the value is down here. And can you see that it doesn't matter how thin I make my delta band around this point? That delta band is always going to contain some fractions and some non-fractions. So it's always going to contain some points up here and some points down here. So if I just set my exclusion zone to be a half, say, then either I'm setting this, the exclusion zone here, or here, depending on whether x was rational or not. And either way, if I set it up here, I'm going to get values dotted around down here. If I set it down here, I'm going to get values dotted around up here. So it's discontinuous at every point. Now, as a challenge, can you think of a function that is only continuous at one point? Well, how about pretty similar to this one, but f of x is equal to 0 for x quotient and x otherwise. So now all the real numbers that are not quotients are getting put on this line, and all the ones that are getting put on the x-axis. And this function is continuous at 0. Because it doesn't matter what band you specify here, you're always going to be able to make the box whatever epsilon you specify here. You can set delta to be that epsilon, make a square, and the function is within that square. There's another nice way of visualizing continuity that doesn't confine itself to two-dimensional graphs in the same way that we've done. So maybe a nicer way of visualizing it, which is to have a function that maps a domain to a target, and specifically it's mapping our point x0 to f of x0, and we're saying that for any epsilon ball around f of x0, so that distance there is epsilon. So for all epsilon ball around f of x0, can you complete the sentence? There exists some delta ball around x naught which maps to within it. So pictorially you can think of there as our delta ball, and this delta ball is going to map to somewhere within that epsilon ball. And this leads us onto a metric spaces definition of continuity that says a function f which maps a domain to a target is continuous if and only if the pre-image of any open set in the target is also open. So we have our domain, we have our target, we have some open set S in the target which is open, and the pre-image of S is the elements of D that map to S. Pre-image of S. Yeah, T is the image of D, so D is the pre-image of T. Yeah, if I have a point X which maps to a point f of x, then f of x is the image of x. Similarly, x is the pre-image of f of x. So this definition is of interest because it doesn't talk about individual points. It just talks about sets. So let's show that this definition is equivalent to this definition. So we need to go both ways. We need to start by supposing our map is continuous, and then proving that this follows, and then we start by supposing that this is true, and then showing that therefore it's continuous. And before we go any further, we need to define what is an open set. An open set, a set S, is open if for any point in it we can make an epsilon ball around that point that is completely contained inside our set S. So, as an example, let's look at the points inside the unit circle in R2. So, here's our unit circle. We're only interested in the interior. So I should maybe dot that line to show that we're not interested in the boundary. So can you see that any point inside that unit circle, we can draw a little circle around it that is completely contained in S, we could say vectors where the length of the vector is less than 1. Maybe vectors in R2, 2D Euclidean space. So that is an open set. Okay, let's start by supposing that for all open S in the target, the pre-image is open, and we are required to prove F is continuous. So we have our domain and our target. And we have a point here mapping to a point here. This is x mapping to f of x. So let's take an epsilon ball around f of x. I'm going to draw it big just so I get a reasonably clear diagram. And let's look at the pre-image of that epsilon ball, which must be somewhere in the domain. Well, we're supposing this pre-image of an open set, because that epsilon ball is an open set. It's the points where the distance is less than epsilon from f of x. So that's an open set. We know the pre-image is an open set, so this is an open set. What is an open set? Well, it means every point in it you can make a ball around that point that is completely contained in the set. And that's going to be our delta ball. And that delta ball has to map to somewhere within the epsilon ball. This is the image of the delta ball. Maybe if I use a different color. So that's the image of the delta ball. Now it should be obvious that f is continuous at x, because we've shown, given any epsilon ball, we have found a delta ball that maps to within that epsilon ball, which is exactly what we have here. So, done. Okay, so now let's go the other way. Let's suppose that our function is continuous. So we're required to prove that the pre-image of an open set S in the target is open. So again, let's draw our domain and our target. And we've got an open set here. In our target, and here's the pre-image. And we wish to show that it's open, so i.e. any point has a ball around it. That's completely within the set. So let's consider X in the pre-image of S. That's going to map to f of x in S. So we consider some open set S in the target. And we're required to prove its pre-image is open. In D, i.e. for all points in the pre-image, we can make a ball around that point. An open ball around X. And that open ball is in D. So let's consider any point in this pre-image. And X maps to f of X, which is in S. Now, using the fact that f is continuous, that's saying that for any epsilon ball you pick around f of x, you can find a delta ball around x, which looks like we're practically done. So you know S is open, so around every point you can make an open ball that's within S. So let's do that. Let's make an open ball around f of x that's in S. It has radius epsilon, say. Now, using continuity, you know you've got a ball of radius delta around X that maps to within that epsilon ball. Now, S is open, so that means we can make an epsilon open ball around f of x. which is completely contained in S, and because f is continuous, for any epsilon ball around f of x, there exists a corresponding delta ball around x. Which maps to within that epsilon ball. So this delta ball maps to within the epsilon ball, which itself is completely within S. Therefore, the delta ball must be within the pre-image of S. So I'm going to write the delta ball maps to a subset of S. Therefore, it must be within the pre-image of S.